Hi, welcome back to Autonomous Mobile Robots. My name is Paul Fergale and I'll be your teacher for this segment on wheeled locomotion. So I'm going to start by talking about the difference between manipulator kinematics and wheeled kinematics. I'll introduce the basic wheel types that we use on mobile robots, and then talk about the different categories that we use to characterize the motion of wheeled systems. So let's start by looking at why we want to build wheeled mobile robots. On flat surfaces, wheeled locomotion is 1 or 2 orders of magnitude more efficient than legged locomotion. And on softer surfaces, the efficiency of wheeled locomotion suffers. However, it's still the standard choice for mobile robot applications, just because of the greatly reduced technological complexity of building, maintaining, and controlling wheeled robots. As we've seen in the context of manipulator kinematics, both the forward and inverse kinematics problems are well posed. So forward kinematics, recall, is given a set of actuator positions, determine the corresponding pose of the end effector. And inverse kinematics, given a desired pose of the end effector, determine the corresponding actuator positions. Now, it's not that straightforward when we try to apply this theory to wheeled mobile robots for a number of reasons. First, not all degrees of freedom of a wheel can be actuated or can even be sensed. Motion around these axes cannot even be sensed sometimes by the robot. For example, this is a graphic you'll see a lot. It's a sort of a top-down view of a differential drive robot. So these rounded rectangles are a top-down view of a standard wheel. Okay? And this ball here represents a spherical wheel, so we often just ignore that. It's just like a support point for the robot. And if you think of this wheel on the left side of the robot, put a coordinate frame there that's set at the contact point. And if you think of rotation around this contact point, there's no encoder there, and the robot can't actually even sense that. So there's a degree of freedom there that can't be sensed by the robot. But not only that, wheels can also impose differential constraints, so constraints on the derivatives of motion that complicate the computation of kinematics. And so if I give some notation here, so r is the radius of the wheel, phi dot is the rotational speed around the wheel axle, and I can write down this sort of set of differential constraints. So x dot, the motion in the x direction in the wheel coordinate frame, should be explained by the turning of the wheel, and that's phi dot r. And y dot, in this case, if we assume some kind of ideal wheel, is 0, because the wheel cannot sideslip, so it can't go in that direction. And these are really important, so we actually have names for these constraints. You have the rolling constraint, so motion in the x direction should be explained by rolling of the wheel, and the no sliding constraint. So in an ideal case, the wheel cannot sideslip. And so instead of kinematics, we talk about differential kinematics. And we still have the forward and inverse problems, but they're slightly different. For differential forward kinematics, we say given a set of actuator speeds, determine the corresponding platform velocity. And in the differential inverse kinematics problem, you say given a desired velocity for the platform, determine the corresponding actuator speeds. So I'll take a moment and just go through the basic wheel types and talk about what degrees of freedom they have. So we start with A, which is a standard wheel. And this has essentially 2 degrees of freedom. The first is turning around the wheel axle. And the second is free rotation around the contact point. And standard wheels can be either steered or rigidly fixed to the robot base. The second type of wheel is B, the caster wheel. And this is similar to the standard wheel, but you have this steering axle here and then an offset to the wheel center. And this now has 3 degrees of freedom. So again, you have rotational rate around the wheel axle. Again, you also have free rotation around the contact point. But in this case, you also have rotation around the caster axle. Next, we're going to look at the Swedish wheel. Now, these diagrams might be a little hard to see, so I actually have a picture here. So the Swedish wheel is actually a wheel with small wheels embedded in it. And this again has 3 degrees of freedom. So first you have, once again, rotation around the wheel axle. You also have, again, free rotation around the contact point. But in this case, you also have rotation of the small wheels. And so in this way, you can get the sort of this translational degree of freedom that comes from the rotation of these little wheels. And you have Swedish wheels with different angles. If you look back at this slide, we have the 90-degree Swedish wheel where the little wheels are sort of 90 degrees to the wheel, and then the 45-degree Swedish wheel. The final wheel is that we'll look at is the spherical wheel here, and this of course has 3 degrees of freedom because you can rotate essentially around any axis. Now, because of these differential constraints, different configurations of wheels on a robot base produce different possibilities for motion. And so a large part of what we'll see in the next few segments are tools for categorizing different systems. At the highest level, there are 2 different categories, holonomic and non-holonomic. Now, you may have encountered the concept of holonomy in other courses, so I'll try to be clear. In mobile robotics, the term refers specifically to the kinematic constraints of the robot chassis. For a holonomic system, differential constraints may be re-expressed as constraints on the robot's pose. The robot is able to move instantaneously in any direction in its workspace. But for a non-holonomic system, this is not possible. So it's not possible to take the differential constraints and re-express them as a constraint on pose. Now, let's get some intuition about this by considering some examples. The first example is a bicycle with fixed steering. So again, these rounded rectangles are wheels, so we have 2 non-steerable wheels. Now, when you do this, remember we have these no sliding constraints, which are this way, and they intersect at a sort of instantaneous center of rotation. And if you do this, the workspace of the robot collapses to a single degree of freedom, and that is a circle. The result is that the differential constraints, these no sliding constraints from each of the wheels, those can be re-expressed as constraints on position. So in this case, we know that the back wheel of the robot will always lie on this circle, and that the heading of the robot will always be tangent to the circle. And further, in any configuration, it's possible to choose wheel velocities that move the robot any direction within the workspace. The second holonomic example is sort of a more common one, just so you can imagine this. You can probably find one of these to play around with, and that is the office chair. Now, we saw that caster wheels, because of the rotation around the caster axis, have 3 degrees of freedom, and so they impose no differential constraints. And so, as you know from interaction with these office chairs, they can instantaneously move in any direction or rotate around the center at any time. The next is a non-holonomic example. So this is a very common design for robots that we'll see again and again in these segments, which is the differential drive robot. It has 2 non-steerable standard wheels aligned on a common axis. So the mobility of this robot is pretty similar. It's actually a bit more than a car. So if you've driven, you know that a robot with this kind of mobility can really reach any pose on the plane. So given any coordinate frame on the plane, I can come up with some motions that will drive the robot there so that it's able to achieve that. But it still has this no sliding constraint. So we know that the robot cannot instantaneously move sideways. And so regardless of the configuration that the robot is in, instantaneous motion in the Y direction is not possible. And in fact, this is why parallel parking is hard. So if I have a lineup of robots here in a parking lot, and we want to park in there, we know it's possible. But again, you're going to have to do you can't move directly sideways. You have to do some interesting motions to pull in and achieve that pose. Okay, with that, we've given a basic overview of wheeled locomotion. And in the coming segments, we will look at the relationship between a specific wheel configuration and the platform speed. Thank you.